In the previous videos, we talked about osmosis, the movement of water, and tonicity, what happens to a cell when water moves. And two main terms surface when we talk about these two things. The first is something we call osmolarity, and the second is tonicity. Okay? So osmolarity is how much stuff is in a solution compared to another solution. So we're just going to put how much stuff. Okay? And when we look at this, there can be three different options, right? We can have a hypoosmotic solution, okay, which is less stuff. We can have an isoosmotic solution, which is same amount of stuff. We can have a hyperosmotic solution, which is more stuff. Okay. Tonicity, we've already been through, is the cell's response when placed in solution. And do you remember what those three responses were? Or what the solutions could be, right? So you can have a hypertonic solution. And what happens when a cell is placed in a hypertonic solution? The cell shrinks due to water efflux. Water moves out of the cell. Okay? We can have an isotonic solution. And that is no change in the cell due to no movement of water. Or we can have a hypotonic solution. And that's where the cell swells due to water influx, moves into the cell. Okay, so those are your three options. So the question is, right, it's very easy to think, well, if water moves based off of osmolarity, then the osmolarity dictates the tonicity, right? So one might be quick to say that hypoosmotic solutions are hypertonic and isoosmotic solutions are isotonic. But let's go take a look at this for a minute. Let's take our box. Okay, and in our box, we are going to put a solution of stuff, and it's going to be 286 milliosmoles. Okay, and I have a cell, and it has a solution of 286 milliosmoles, or an osmolarity, right? So these two osmolarities are the same. So they would be isoosmotic with one another, right? They're the same osmolarity, okay? But remember, osmolarity only tells you how much stuff is in the solution. It doesn't tell you anything about what that stuff is, right? So what if it was a molecule, and we'll call it green? 286 milliosmoles of green dots. And what if this was, the cell was 286 milliosmoles of red dots? But then what if I told you that the cell had a channel on it? And that channel made this cell permeable to green dots. And if I put this cell inside of this solution, what's going to happen? Right? If we draw this as two boxes instead of a box and a cell, we'll just call this cell and this the box. I have 286 red, and then over here I've got 286 green. But I have a green channel. Okay? So if this happens, the green will move from the box to the cell. So if green moves out of the box and into the cell, what happens to the osmolarity of the cell? It was 286, right? But now I'm putting more stuff. So the movement of green causes the increase in osmolarity of the cell. So let's say that, for the sake of my argument, it goes up to 300 milliosmoles, and then the cell goes down to 272 milliosmoles. What's going to happen with the water that's also inside of these cells in this box? Water is going to follow the stuff, right? So water will move into the cell. So when we started, right, we said that this was an isoosmotic solution, same osmolarity. But now we're saying that water influxes or moves into the cell. And so that's going to cause the cell to do what? It's going to cause it to swell. And so if that's the case, then the box represented a hypotonic solution. Okay? It represented a hypotonic solution. Right? So it was isoosmotic, but hypotonic, right? So from this, right, we can clearly now see that osmolarity does not equal tonicity. Okay? What we need to account for is permeability. What is the cell permeable to? Okay? And so a lot of times we'll refer to things that can move in or out of a cell when placed into a solution as a penetrating substance, right? And things that can't as non-penetrating substances. So you may see this as a lot of physiology labs will run an osmolarity or tonicity lab using things like sodium chloride, salt, and urea, because salt is non-penetrating and urea is. So think about, right, what would happen if I had six different solutions, right? I had, let's go with isoosmotic sodium chloride. I had hypoosmotic sodium chloride. I had hyperosmotic sodium chloride. And then I had isoosmotic urea. I had hypoosmotic urea. And I had hyperosmotic urea. Okay, remember, urea is penetrating, meaning it can move in and out of the cell. And I'll tell you that red blood cells have low urea. Okay, but sodium chloride is non-penetrating. It cannot move in and out of the cell. Okay, so let's do the isoosmotic ones together, right? So we have trying to get a color here, isoosmotic sodium chloride, right? So osmolarities are the same. So we can think about this as our box, right? Is we have X over here, we have Y and X over here, right? Because the osmolarities are the same. So let's consider this the cell and this the solution. Okay, so if the osmolarities are the same and nothing can move through it, right, will water move? Right? No, it won't. So this has no water movement. So what do you call that when there's no water movement? That's an isotonic solution. Now, let's look at isoosmotic urea. We'll draw this one a little bit bigger. We're going to do it in, we'll do the gray box. Okay. Sort of like so. Do a little call out for it. And we'll do our division. And we're going to do cell over here. Urea solution over here. Okay. And the cell has very little urea in it. But let's assume, right, because it's isoosmotic, it's got other stuff, right? So we do 286 milliosmoles of stuff. And then over here we have 286 milliosmoles of pure urea. Okay, but urea is a penetrating substance. So the urea will move into the cell. Right? And so if urea moves into the cell, what's going to happen? Your osmolarity is going to increase inside of the cell. And what's going to happen? Water is going to follow the stuff, much like the example that we used earlier. Right? So if water moves into the cell, right, the cell is going to swell. Right? And so because of that, this is a hypotonic solution. So isoosmotic urea is a hypotonic solution, but isoosmotic sodium chloride is an isotonic solution. So osmolarity, tonicity are not the same thing. That's going to have great implications on things like, should you drink Gatorade? Or what sort of solution do I give a patient who's dehydrated? So until next time, I'll see you later.